Good morning. So one thing I quickly want to say here is that your attendance on CYMS is like automated with the Blackboard, right? So if you don't attend your this lecture at least 30 minutes, 30 minutes doesn't mean 29 minute and 59 second. 30 minutes means 30 minutes. Then your system automatically marks you absent, right? I have no say in that. So please mind that thing. Although our lecture is 40 minutes plus, so you should be present at least 30 minutes. Okay, so let's see what we are doing last time. If you guys have any question, you can ask now. Otherwise I will just resume what we were doing yesterday. Any question? Okay, so I think this screen should be visible to you. We're talking about uh, ensemble. Let me see my presentation. Okay, yeah, so what we were doing is, yes, so we talked about uh, representative points in phase space uh, of a gaseous system, for example. Otherwise, this is in general too. And just give me 1 minute. Okay. So we defined this density of representative points in a phase space. That's why it's a function of Q and P as well as time also, right? So then we define certain things that how if I have volume element, which is something like this, which I told you here, right? If this much volume you consider out of your phase space, then how many number of representative points will be there? So the number of representative points, just multiply this volume by the density. That's how density function is basically defined, right? So we also define, this is very important quantity, and usually you do these things in quantum mechanics also when you calculate the expectation value of some observable, right? Here like this f, uh, which can be a function of q, p, or maybe t also. So the ensemble average of this guy is this is how it is written, right? So here this rho is occurring. This is the density of representative states in, you can say, uh, volume element d omega, if you would like to represent this volume, this small volume by d omega. So this is the volume element, number of points in phase space at each location q and p. You need to multiply that by respective number of points, and then just sum over whole of the volume, of course the allowed volume region in phase space, and just normalize that. That's how ensemble average is defined, right? And yes, yeah, this is written, I told this thing last time also, that in general it can be this, the ensemble average can be a function of time also. This time dependency in f will come due to the time dependency of this my rho on t, right? Because I wrote somewhere above that rho is a function of time as well, right? So you can assume that density of representative states in phase space at a particular q and p location may vary with time also. This is the most general way we can say. Okay, so somebody's Rahul is saying, sir, what's the difference between time average and ensemble average? Rahul, I think this is something I told yesterday, but I can repeat it also. That so if you observe the system and let the time pass, right? So you will observe your system at different instants. Okay, and then what you are going to take is the time average of that particular property. You, that property can be anything, any physical parameter of the system. I'm not getting into that particular thing, but any property related to the system. It can be density, not density of the representative points, but density, your chemical potential, pressure, temperature, right? uh, and so on. So the time average, you observe same quantity over a span of time at different instants. Although I explained in my last lecture also, whenever you are going to measure anything, the system is switching so fastly in between different microstates. Actually, you measure the time average uh, of that particular quantity, right? So, but now we are representing each time instant the system in a particular microstate, we are representing each such microstate by a representative point in my ensemble, which are the points or representative point in phase space. So if I now take the average at a particular instant over all those representative points or over the ensemble, that's called the ensemble average, right? So both should come out to be same. That's how that's, you can say, foundation of this ensemble theory. We assume that this average is same, so that's how we progress. Hope that clears your issue. Okay, so then we talked about one special scenario when my row doesn't depend upon time explicitly. Okay, do remember this word explicitly. Many of you may not get this, but this is something like, because I wrote my row as a function of q p, but it doesn't have t in it. Okay, although my q is a function of time and p is also a function of time, so the dependency of row on time is via q and p, so that's okay. But if it doesn't depend upon time directly, then I can safely write that curly row by partial differentiation, not full differentiation. Still my d row by dt will be non-zero, right? And you all should be able to write that what d row by dt would be if row is a function of my q, p and t, that by chain rule. Okay, but I'm just saying that curly row by curly t is zero, and if this part is zero and row doesn't depend explicitly on time, so it means it doesn't involve time here in this expression. In that case, my ensemble average will be independent of time. It doesn't have, and such ensembles are generally termed as stationary ensemble, because of the ensemble average of any observable corresponding to such ensembles is independent of time. That's what this equation means. And basically in such a scenario, or the stationary ensemble, I would mean to I would like to call such situations equilibrium state of the ensemble. Okay, because in equilibrium state, if you measure any parameter, that is not going to vary over time, right? Okay, so this was a bit review what we did last time. So let's today I'm going to start one important topic, right? It has a great consequences in this ensemble theory also. So this is termed as the Lively theorem. Okay, so this we are going to start discussing today, right? So I try to draw some figure also. I'll explain what this is. Okay, although these are not in your book, but I'm trying to I'll try to explain this. Try to be with me, okay, and ask questions. That is how you are going to learn. And obviously we will see its consequences also, that basically the various, you can say, consideration that how my Lively theorem is going to obeyed by ensemble is going to decide whether my ensemble is a micro canonical ensemble or it's a canonical ensemble. Okay, so and these two topics are like going to be central of part of your this unit one. Okay, so if you remember, so we were representing our microstates of my system by their QIs and PIs, as one of the student rightly pointed out, that the state of my system will be given by so and so positions and so, he said velocities, but more general would be momentum, right? Because my two different gas molecule can have same velocity, but they will be in different microstates if they have different masses, right? So mass should also come into the picture. And we know that when we are talking about generalized momenta, generalized you're going to say coordinates, so this momentum is always not mass time velocity. It may be angular momentum, then there will be moment of inertia, or like action angle variable kind of thing, then your this p is something else, right? But those are like deeper details, but that's fine. If you, for simplicity or understanding, you consider this to be position and this to be momentum, that's fine, just for understanding. But keep it in mind that they have more general meaning than that. So what I was saying is that of course your QIs, I means for first particle, second particle, third particle, and so on. This I varies from 1 to 3n. Okay, because Q1, Q2, Q3, they both will be for first particle basically. So Q1, Q2, Q3, you can think of first particles XYZ. That's why it's 3n for n particle. Okay. So of course, a particle are going to move here and there, and of course this they are going to evolve with time. These both. That's the meaning of what they are function of time. And of course, the governing equation would be equation of motion. Of course, the Hamilton equation of motion, right? So those are the kind of thing which govern these classical systems. And what we did to build this ensemble is that we took at each instant, for example, instant number one, where I had time t1, then instant number 2, instant number 3, instant number 4. So my system was switching between various qi's and pi's. At each instant, each microstate can be represented by a dot or a point in 6-dimensional space, what I termed as phase space, right? So these points are basically representatives. So each arrow means each instant of time. So there are so many points, and each point is representing a different microstate. So these points jointly, I term this group as the ensemble. This is what I mean by. So if I take the, as Rahul asked, what is the, if I take the average over this evolving time, so that would be the time average. If I take the average over this ensemble, that's the ensemble average. And essentially they both mean same. That's the foundation of ensemble theory. Repeatedly I'm saying this again and again, right? So these points. Now, of course, this is at one instant, right? Because this we now forgot about the time dependency of these representative points. Now we mapped each instant to a point in phase space. Now this is ensemble. Now time is no more there in this ensemble. But of course, if you further allow time to move, even these representative points will move in phase space. This we saw, if you remember, when we draw the trajectory in phase space for pendulum, for you can say simple harmonic oscillator in our classical mechanics course, right? So they all are going to move here and there. So these ensemble representative point, even they are going, bound to like a move in certain predefined trajectory, of course governed by the Hamilton equation of motion in phase space. So this whole swarm, which I told yesterday also, this swarm is this group, like a group of flying birds. They are also going to move here and there in phase space under a limited region, as this dictated by your macro state, the volume and energy. Because I told you volume is going to put constraint on qi's and energy is going to put constraint on pi's. Only allowed region is which are satisfying these constraints. Okay, so now this I just built up the, you can say, foundation, that what we are going to consider now. Now be with me, try to understand this. This is not very hard. So what I'm going to consider is I'm going to take a very small element, volume element omega. So this volume you are looking at, although I drew it on a two-dimensional surface or maybe three-dimensional, but try to imagine this is the volume from phase space in six-n-dimensional, in six-n dimension. Okay, so I considered this volume. It is bounded by a surface sigma. So sigma is the surface bounding this volume omega. Okay, and a very small element of even this volume, if I try to consider this a small element, it is not you can say necessarily should be a cube, which immediately run into the problem, which you can see that it's actually not a three-dimensional space, it's six-n-dimensional. So this small element part of this volume omega I'm writing as d omega, and d omega is written something like this. This you are going to see again and again, the volume element in this volume omega. Now the rate at which representative points are increasing in this, for example, there are representative points everywhere, right? Because this is a part of the full allowed phase space volume. Everywhere there are you can say representative points. They have a tendency to move in and out of this you can say volume omega, right? So they are entering, might be leaving. That is the possibility. Both the possibilities are there, but we are looking at them one by one. Okay, so that we can like handle them with care, of course, right? So this you must understand how this could be a rate of the increase in number of representative point in this volume. Why? Because rho is the local density. Mind it, rho is the density at this omega is at certain location q and p, right? So in phase space, so this omega is the density at this volume. So if I multiply this volume by this a volume element, for example, if I just consider this small volume element d omega, then this will be the number of representative points in this small volume d omega. And how this is changing with the time, only partially, mind it, only change with the time I'm interested in. I'm not looking at change in this number of representative point as I vary q and p. That can also happen if I move in phase space at various locations q's and p's, but that's not what I'm doing right now. Q and p's are like fixed. I'm looking in the neighborhood of q and p. So how this is going to change with time, that can be easily written. And if I just integrate this over whole volume, this omega, so I will get total number of representative points, how their this number is changing with time. This is how I'm going to write it, right? Any question with this? I don't think it's very hard to see. Okay, now just consider this cylindrical picture. Okay, and here I drew a velocity vector. This is the velocity of representative points in phase space, and mind it, it's not a typical velocity. It is going to be governed by this thing, and be careful here, it's not equal to, it's equivalent. So q dots and p dots, these are the component of my velocity vector in phase space, and if you remember, these are basically dictated by your Hamilton's equation of motion. Okay, so of course this v vector, I mean to say this, it's not a dx by dt or dq by dt kind of thing, mind it. So these representative points in this small volume only, just for drawing purpose I made it big, otherwise almost every dimension is vanishing here. Okay, so and I'm considering a very small surface area of this cylinder here. This is d sigma, and unit vector perpendicular to this surface is n cap, and jointly n cap d sigma is nothing but d sigma vector. This is something similar to what you define electric flux, magnetic flux kind of thing in your 10+2 level also. Okay, so now if I observe this whole system for dt time, okay, then the number of particles or number of representative points which can move out of this you can say cylinder will be equal to the volume or equal to the density rho within this volume v dt times sigma, right? So that's going to be the number which can leak out of this. Of course that is going to decided by the angle between this v vector and n vector. Okay, so v is inside, then it will be negative. If v is going outside, it has certain angle less than 90 degree, then that point will leak out of this volume omega. So how that number can be written, it's written here, or I would say the more correct version of this would be let me go to next page. So it's written somewhere here. So I'm basically taking this integral over surface, of course, because here in this figure the integration of this leakage of representative point number is from this surface, so that's why this integral is over surface. Okay, so the density is appearing there, and the velocity vector is appearing there, and of course the d by dt factor is inbuilt inside this. Okay, because that has gone because this vdt was there. Okay, so yeah, so now we can kind of use, if you remember, Gauss divergence kind of theorem, which you usually used in your 10+2 level for converting surface integrals into volume integrals, right? So instead of, you can consider this whole to be a vector dot this surface area vector. This can equivalently represented by integral of divergence of same vector, which is written here, but this divergence is not your lower class del dot some a vector, mind it, right? So this del was curly by curly x I cap, curly by curly j cap, and so on. Basically over there it was x y z, only 3 coordinates were there, but here we have 6 n coordinates, if you remember. Okay, so accordingly this divergence will be defined later, I'll tell you, and vector it will stay there. So instead this you used to write it as divergence of a vector, right? So there is no need to put dot anywhere. So that's what I did here. So divergence of this whole vector, as of course this is a rho is a scalar number. It is a function of your qpt, that's okay. V, again this velocity is a generalized velocity in phase space, it's not the dq by dt kind of thing. And of course now you change your surface integral to volume integral over whole volume omega. Okay, this is how we define the divergence of this vector. So it's quite similar how you define in your lower class. Here you were you doing this. So I would write like this: curly q1 of a uh, x plus curly a y by curly q2 plus curly a z by curly q3. Basically I wrote here the components ax, ay, ez, and q1, q2, q3 are basically x, y, z. So this is how you do over there. Here instead of doing this I'm doing like this, so you must appreciate. So basically qi dots are the only velocity components which depends upon position coordinates, or I would say the canonical position. Okay, or generalized position coordinate. This rho is being multiplied everywhere. don't bother about that. And then differentiating that with respect to position. But this velocity doesn't have only qi's, it also has pi's in it. Okay, so this definition we have to extend like this. This is how the divergence in phase space is defined, right? So any question with this you can raise now or maybe later also. Okay, so this is our important result we are going to stick with. I'll tell you more about this thing. So now, because this is a kind of conservation of number of representative points in phase space, because there is, I would say, no source or sink of the representative points, or the number of ensemble members can't change in phase space, right? So the number of, or rate of increase of the representative point in phase space should be equal to negative rate of decrease in the number of representative points. So this is basically the number of points of representative points entering that volume omega, and this is the number of representative points leaving the volume element omega in a given time dt, right? So they should be equal, and actually I'm saying their sum should be zero. The total entering, total leaving is equals to be zero. So if you just recombine them, keeping this omega out, so you will you can easily write this thing, right? Now this equation is true for any volume omega in phase space, because we have not attached any importance that where we are like going to consider this omega. This is true basically for any volume element omega in allowed phase space region. So it means this can be true equal to zero only if this integrand is identically zero for every d omega, right? It should be zero. So if you put this thing equal to zero, this is nothing but if you now can see, this is the equation of continuity. But this is the equation of continuity not for liquid or maybe for electromagnetic field but this is the equation of continuity for the number density of representative points in phase space. Okay, mind it. So this is actually a byproduct of this derivation, but I'm not that much interested right now in this, but I'm going ahead with this thing. Any question with regard to this? I'll pause maybe for 10 to 15 seconds, and if you want to ask, you can unmute or type in. I'm waiting. You guys should raise question, because soon you are going to like go for your MST1. So this is kind of preparation. No questions as usual anyway. So let's move ahead. Let's see what consequences we can see for writing this thing. And let's see if we can have something with the something important coming out due to the divergence of rho v as defined here, because we have not used this expression as of now, right? So we just came up with very simple thing. These many point entering the volume omega, the rate of increase of number of representative point, this is how much they are leaking out of the volume, and they should be equal and opposite to each other, right? Because there is no source or sink in that volume omega, in fact anywhere in phase space. So this number has to be conserved. So this immediately give us continuity equation for number density. Okay, or density function. So let's see what we can say about more about this thing. If you see, let me write a few things now. We define the divergence. I would like to write it because it's interesting, right? And we saw similar thing in classical mechanics in lower class also, the last course I would say, right? This was defined something like this. So it's curly by curly qi rho qi dots. Okay, so because I'm just, this row is staying as such there, but this velocities, which component I am taking? The generalized coordinate time derivative. Okay, and I'm just differentiating it with respect to the generalized coordinate. This is how you do your uh, divergence is. So then of course, because your v is also a function of pi, so this has also go with pi's dots, right? So this of course, and how I is running over full degrees of freedom, 3n. So 3n terms here, 3n terms here, basically there are 6n terms, Okay, similar to your three-dimensional divergence is only three terms because that's only three-dimensional. Okay, so now what we can do is we can apply a u into v kind of formula. So I will have four terms actually. So I will have summation over I. Understood, I is running from 1 to 3, and I'm not going to write even I again and again. These are written in notes and they are like available to you on Blackboard. So curly by curly qi row as such here, and qi dot is there, right? Plus I'm writing only one term out of this because I'm going to apply u into v formula on these two. Then plus second term would be curly row by curly qi, not qi, pi this time, pi and pi dot. So this is one of two out of the four term, and rest two I'm going to write here. So they will be curly qi dot by curly qi into row plus curly pi dot dot by curly pi into row. In fact, this row can be taken out also of this, right? Okay, so let me remove this from here. And this is kind of one homework which I kept for you people to. Just a minute. I don't know which eraser I have selected. Okay, I'll write this again. So what my idea was to write row here because row is independent of these I indices. So plus curly pi dot by curly pi, right? So this term, okay, let me take another color just for your, you can say, understanding. So what I'm saying is this term and this term including row, this is basically coming out of this, but I wrote them separately, I clubbed them separately. Okay, so what is the homework for you? It's your homework that prove that this is going to be 0. Okay, it's not hard to do, just use equation of motion for qi and pi dots, you will get that they are going to cancel each other. Okay, so what this upper equation is saying, this equation is just equals to summation over I and curly row by curly qi, and qi dot as per Hamilton equation of motion is nothing but curly h by curly pi. Hope you remember. And similarly, next term is curly row by curly pi, and this pi dot is nothing but minus curly h by curly qi. And if you remember, these are nothing but Poisson's equation. Okay, hope you remember that. So this is Poisson equation of rho with h only. So it means that my divergence of this guy rho v, this is nothing but a Poisson equation of rho with Hamiltonian. This has to happen, right? So now how we can utilize this? Let me show you here. Yeah, this is everything actually wrote nicely. So you can see them later. So this is basically nothing but equation of continuity again, but instead of divergence of rho v, I wrote these things expanded, and this was excuse me. I thought that you will do this as homework, although this is just a couple of lines. Okay, so let's so now this part I already proved, and so it means you can write, forget about this part right now. Okay, don't look at this, but this thing is just curly row by curly t. It's coming from equation of continuity, and this divergence of rho v, we just proved that it is nothing but the Poisson bracket with the Hamilton. So this is equal to 0, right? So this is the, you can say, modified version of your equation of continuity, and this equation is basically termed as the Lively theorem, Lively's theorem. Okay, and how it is the full differential of rho, this is again kind of a homework for you guys, right? Although this we did in classical mechanics course also, right? So because only hint I can give you is that your rho is a function of q, p, and t. So now apply the chain rule to write d rho by dt. So of course you can see there will be one term of curly rho by curly t, but there will be terms like curly rho by curly q, curly dq by dt, and then curly rho by. Although I'm telling you the answer, but this is how it can be proved. So this is basically the Lively theorem. Now. It has certain consequences for the ensemble under consideration. Okay, what are those consequences are, let's see quickly. Basically this equation, irrespective of what is happening, always tells that the full derivative, time derivative of this density function is going to be 0. Okay, it doesn't matter whether your rho explicitly depend on time or not. Okay, so rho, even if it is a function of time or it is not a function of time, its full time derivative is going to be 0 always. This is a bit strange. Actually, this is one of the consequences of this Lively's theorem. It just says that if you you can say sit along a representative point as it moves in, I would say, the phase space, the density, you would see the number of representative points which you see around you, that is going to be constant. It will not vary. Okay, so other way around, I would say you won't experience that it is moving basically. Okay, so this is you can say one of the consequence of this Lively theorem. Another idea is, now suppose you are considering one special kind of density function rho, where rho doesn't depend upon time explicitly. That I mean to say by that is that curly rho by curly t. This is what we saw in last lecture. In fact, in the beginning of today's lecture also, that then my curly rho by curly t is going to be 0. If this part is 0, then of course this Poisson bracket must be 0 in order to satisfy this Lively equation. Then what does that mean now? So rho with h Poisson bracket is 0, we can expand it like this, right? Now I know that my qi dots and pi dots, they are not 0, right? Because they are what we get out of equation of motion. It means my these two quantities identically should be equal to 0. Curly rho by curly pi and curly rho by curly qi, they should be equal to 0. It means that my rho should also be independent of q and p. Okay, so for a stationary, you can say, ensemble where your rho doesn't explicitly depend upon time, one way to satisfy Lively equation is that your rho must also be independent of q and p. It means your rho is basically, although we can write it as a function of qpt, but it's a constant, right? It doesn't vary. So under this special condition, this necessitate that this Poisson bracket should be 0 and Poisson bracket should be 0, necessitate that rho should be independent of p and q also, because only that's the scenario that these two are going to be 0, because qi pi dots, they are not 0, right? That's the velocity with which your representative points are moving in phase space. Okay, maybe 5 minutes more we are left with. Let's try to wind this up. Let's see for a few more. Yeah, that's what I said. Yeah, and in such a scenario, the ensemble average, as asked by Rahul today. So the ensemble average, if you remember, that rho which was appearing because it's a constant, so this will get out of the integral. So your ensemble average is going to get a very simplified, you can say, expression which looks something like this. Just integrate your function over all volume elements over whole volume of your volume under consideration, and just take average out that over same volume. So that's the ensemble average of your any observable f. F in itself can be a function of q, p, and so on. It depends. Qp, it will they will have qp in it, and maybe time dependence may come through sorry, dependency of q and p on t, right? Because we nowhere said that q and p can't depend upon t. Sorry. Now further thing is that yeah, so this for condition number 12, which is which I mean to say that this rho is constant. It has these although I think I said these thing one and another way, but let's see what these points I have written down. Any member of the ensemble is equally likely to be in any microstate. Right? So that's the that number density or density function is constant means that everywhere in phase space you have equal number of representative points per unit volume of the phase space. That's the meaning of this constancy of rho. Okay, it means if they are equally spaced, it means all the microstates accessible to the system, they are equally probable. Although we saw this thing earlier also, that this is also termed as the principle of equal a priori probabilities. Okay, and such an ensemble which we referred above, for which my rho is constant, we term such a ensemble as microcanonical ensemble. Okay, and we are going to see a few results in this microcanonical ensemble also, but that's not the only way in which this condition can be satisfied. Let me show you this. Just give me 1 minute here. Right, this is not the only way in which this equation number 11 can be satisfied. There is another way to satisfy this also. Okay, and how that comes, I'll show you here. Yeah, so the other way is how you can satisfy that the dependency of rho on q and p, because I said over here in this on this page, if you see here, this, that I said here that if this is equals to 0, it means because qi pi dots can't be 0, it means these derivatives should be 0, which require that rho can be a should not be a function of qi and pi. That's what forms the basis of microcanonical ensemble, right? But there is another way to make this whole summation over all the i's equals to 0. That can happen if your rho depends upon q and p, but that dependency come due to Hamiltonian, because Hamiltonian depends upon q and p, right? So if you try to write your rho as a function of, when you try to write this curly rho by curly qi, so then you will write your because it's a function of h, so then you will write curly rho by curly h by curly qi. So from there, this you can prove that this is going to be 0. But this is another way to satisfy same equation. Okay, and one form of such a functionality could be something like this, where your rho is proportional to exponential of beta h, where beta is your 1 by kt. We saw it in chapter 1 also. So if this functionality is of this form, that it is beta Hamiltonian, the density function, such an ensemble would also be stationary, because my d rho by dt for this is also 0. Okay, so that's how we define this stationary ensemble. But such a stationary ensemble where my density function is not a constant function, but it's a function of Hamiltonian, such a ensemble would be termed as the canonical ensemble, and this is going to play a major role in canonical in ensemble theory, and we are going to devote much of our time on discussing various aspects like driving the thermodynamics of canonical ensemble, and then we will also be looking at the energy and density fluctuation in canonical as well as grand canonical ensemble also, right? So that would be planned for next coming maybe 5 to 6 lectures, right? So that's all for today. If you have any question, you may type in, else I think you are good to go. Thank you.